We'll start. What is today's date? 6th. So 6th. 22. I expected this to be much smoother. Anyway, it's okay. We'll talk today about first we'll talk about some examples of locally compact groups and their Haar measures. Should I recall what we did last time, or I'll just go forward? I'll go forward. Okay. The first example is the usual one, the most familiar example, which is R under addition. This is a topological group. Okay. And what is the Haar measure here? Usual Lebesgue measure, right? So you have dx, which I'll denote by dx, this measure. And now, because of the uniqueness of Haar measure, we know that the Lebesgue measure is translation invariant, and therefore it has to be the Haar measure up to a scalar multiple, because we saw the uniqueness of Haar measure, right? And this is the first standard example, and similarly you can show for Rn. We shall see a more general statement of this case. Again, you have dx, which is the Lebesgue measure, usual Lebesgue measure. Okay, or I should write bold X. Now there is, obviously there are other examples of this. What is the Haar measure on integers? Integers under addition, they form a topological group. So what is the topology first? The topology is the discrete topology on integers. So this is the topology you get by restricting from Rn. You will get the discrete topology on integers, and the measure is not the Lebesgue measure. The measure is the counting measure, because the Lebesgue measure when restricted to z is 0. Okay, and again, what is the guarantee that this is the Haar measure? Counting measure is invariant on translation, and so it has to be the Haar measure, because we have seen that Haar measures are unique up to a constant. Okay, now this is somewhat a general phenomena. If you have a group G on which you give the discrete topology, okay, then the Haar measure is the counting measure. Okay, again the argument is the same. The counting measure is invariant on translation, and therefore it has to be a constant multiple times the Haar measure. And whenever we talk about Haar measures, we will always be talking about up to a constant multiple, because there is no point in saying the Haar measure, because 2 times or 3 times that is again a Haar measure, right? So even if I say the Haar measure, it is either it will be obvious from the context in the case of if you are talking about R or Rn, then it is obvious, or it should be understood from the context that the Haar measure refers to the usual Lebesgue measure in which the interval 0, 1 has size 1. That is the usual measure that we construct. Has measure equal to 1. The interval 0, 1 has measure equal. So that is the usual Lebesgue measure we construct, right? But when you go to Haar measures, 2 times Lebesgue measure is also a Haar measure. That is what we saw last time. So when you are talking about R, Rn or such groups, it is usually understood that we are talking about the classical objects, classical measures. There is another interesting example, which is this group. You have R, you can say positive reals under multiplication. Okay, positive real center multiplication also form a topological group under the usual topology. Usual topology as in the topology you get from R. On R you have a topology, you can give the subspace topology to R star or R cross, and under that topology, if you consider multiplication, you can easily verify that this is the topological group. What is the Haar measure on this group? And of course it is locally compact, right? The topology is obviously locally compact. So we expect a Haar measure on this group. What is the Haar measure? This is a very interesting exercise to figure out the Haar measure on your own. It's a very interesting exercise. But I'll give you the answer. The answer is the measure of the form dx by x. This is the measure. So what I mean by this is that if you have a set A which is in the Borel sigma algebra, then A is equal to, or the measure of A equals integral over R, or integral over A, the integral over A dx by x. Okay, dx by x. This is the Haar measure on this group. Can you convince yourself that this is translation invariant? Again, the proof is the same. You verify that this is translation invariant, and then by uniqueness this has to be the Haar measure. Okay. So what is translation here? You should remember that x is variable, x is the variable. Okay, so we need to check whether, again, the group is abelian, okay, and therefore left translation and right translations are same. You don't have to distinguish between them. Mu of, let T be an element in the group, we have mu of TA, which is by definition equal to integral over TA dx by x. Okay, this, you do the change of variable, put y is equal to, what is y, t times x. Okay, do this change of variable. If y is equal to t times x, and if you are, sorry, I should take t inverse times x. You do this change of variable, and then if your x is coming from t times a, then y will run through a. Okay, then if you do that change of variable, you will have this is equal to integral over a integral over a, just zoomed in a little bit, yes, what is x now, what is so dy, come on, we'll have dy is equal to t inverse times dx, right? T inverse times dx, because x is the variable, t inverse is a constant. So if you do that substitution here, you will get dx will be now t times dy. Yes, so you will have t times dy by x is also t times y. we'll have t times y. And this t and t will get cancelled. Since we are just dealing with real numbers, you can as well cancel this, you will get mu of a. Okay, so this is the Haar measure on r cross dot. Okay, now let's see. Now all the examples that we saw earlier, R or R plus or R star greater than 0 or integers, all these things, all these groups were abelian groups, and the Haar measure that we saw was invariant under both left and right translation. So the Haar measure that you are getting from left is the same as the Haar measure that you are getting from the right, but this need not always be the case, because in the first lecture I told you that I will be sticking to the left action, and whatever we do will also work for the right action. But at this point I need to pause and I need to tell you that these you will have Haar measures. The existence of left and right Haar measures is not in question. If you have a locally compact group and you are fixing a left action or fixing a right action, you will get the corresponding Haar measures. But whether these two measures will be the same is another question. And at least for me, it is rather surprising that there are groups where these two measures are not same. And hence it is important to understand when these two measures will be same. Because when you are integrating, as we shall see when we are integrating on spaces, we are used to translating left and right without thinking about it, and we will be very happy if that happens, if we are able to translate to the left or to the right without much problems. So those groups have a special name. They are called unimodular groups. I will explain why the name came also. Unimodular groups are groups for which left Haar measure is equal to right Haar measure. Again, up to constants. So I will stop emphasizing that point from now on, and I hope you get it. Okay, but the left Haar measure and the left and right Haar measure, both of them are coming from the same group, and the action is also somewhat very much similar. I am just operating on the left, I am operating on the right, but what I am doing is translating, and to some extent we expect some sort of similarity between some sort of connection between the two, and that is also realized in this following proposition or following lemma. Is that, so you take a lemma, you take left Haar measure on G. G is my topological group which is locally compact, Hausdorff. You take mu, which is a left Haar measure on G. You define lambda of E, where E is a measurable set. Define it to be mu of E inverse. Okay. Now this lambda, it is easy to verify that lambda is right translation invariant. So we should remember that the mu that we constructed is left translation invariant.
What is the exact meaning of E inverse?
Okay, you take every element of E and invert it. E inverse is equal to set of all x inverse such that x is E. You take every element of E and invert it, then I call that set as E inverse, which is a natural notation. If you, so lambda is right invariant. Okay, why? We'll have a quick proof. What is lambda of E t, or this is equal to, by definition, this is equal to mu of E t whole inverse, right? But this is equal to mu of T inverse E inverse, right? But mu is left invariant. So this is equal to mu of E inverse, this is equal to lambda of E. Okay? This makes sense, right? So we need to measure somehow. This relation is somewhat expected because we are constructing very similar objects by left and right translation. So this relation is expected in some sense, but we need some way. So whenever you have a failure of something, for example the failure of a left measure to be a right measure, we need to define some object which will help us figure out how much that failure is. One classical example is the class group. If you, I mean, this is something very close to my heart. If you go to number fields, you will not have unique factorization, and the way to measure how much far away from unique factorization is via the class group. Another example which is coming to my mind is these homology groups. First homology group, if you know the definition, then they measure the failure of something, because you are quotienting out by something which is principal. You have a collection of objects, you have a sub collection of principal objects, and you are quotienting them out. But in both these cases you have groups, but I want to do something similar here, and I want to see, you take mu of A, suppose that A is a Borel measurable set which has positive measure, okay, then you should remember that mu is always left invariant for me. Mu is the measure that we constructed via left translation in the previous lectures, and mu is always left invariant for me, okay. So I want to understand how much of mu of AT varies with mu of A. So you choose an A here and your T in G, okay. No, mu of TA is the same as mu of A. Yes. So mu of AT I don't know, and that is what I want to measure. Okay. Now we observe that, or we shall prove that this thing is independent of A. Another way to state it is that if so given T, you define mu T of A as mu of TA, mu of AT. Here I don't have to assume that A has positive measure to make this definition. I had to assume A has positive measure because I wanted to define this quotient. Okay, but and the reason I am defining this quotient is I need to see how far mu of AT is from mu of A, and one way to measure that is through this quotient. But to make this definition, I don't need.
If T is equals to G, then that means it's just a G equal to identity type.
T is an element. T is an element. T is an element in G. Okay. Right. Thank you. So I make this definition, and this is obviously a measure. It is easy to verify that mu T of A is also a measure on the Borel sigma algebra. But what I claim is mu T is left invariant. Okay. So how do you show that mu T is left invariant? You start with mu T of SA for some element S in G. Okay, this by definition equals mu of SAT. Okay, but I can consider this as mu of S times AT. AT is just another set, and I am translating AT by S. I'll get the same thing, right? But since mu is left invariant, this is equal to mu of AT, which again by definition equals mu T of A. So mu T of SA is equal to mu T of A for every S in G, and hence mu T is left invariant. Now from the uniqueness of Haar measure, mu T of A should be equal to some constant delta of T times mu of A. Because of the uniqueness of left invariant Haar measures. Mu is a left invariant Haar measure which I started with, and mu T is again another left invariant measure, so they can only differ by a constant, and that constant may depend on T, because as T is changing, my measure mu T will also change. Okay, from here, if in particular, if A has positive measure as we took earlier, then mu T of A by mu of A is equal to delta of T, right, which is independent of A, as I have claimed here. Okay, so this quantity is very important for me. This quantity is what measures how far mu is from being a left and right invariant Haar measure. Okay, now this quantity I will call it as the modulus of this group. This is called as the modulus, or it is also known as the modular function. But I will prefer to use modulus because soon we will talk about modular forms which have nothing to do with this modulus. Okay?
Mu is also left invariant and mu T is also left invariant.
Yes, that is what we showed, right? We started with a left invariant measure mu, and then we showed that mu T is left invariant.
So here what you told, that delta T is equal to this thing.
Yes, by the uniqueness of Haar measure. So if you have two left invariant measures, then
This is the mu of AD is the right It's right.
No, we don't know. We don't know.
It's like right translation is also left invariant.
Yes. But we don't know if this is the right Haar measure. We don't know that.
But you said two left-handed Haar measures are equated by something.
Yes. The Haar measure is unique. Unique means unique up to a constant. So if you have two Haar measures, you will be able to find a constant such that one is that constant times the other. I am calling that constant as delta of t, and that constant may as well depend on t. I have only showed that the constant does not depend on a. Okay. So if I want to understand how much my group G is different from being a unimodular group, I need to study this modulus function. The first observation that we make is that, so this is the first observation, if delta of t is identically equal to 1 for every t in G. Okay, I should not write if. Delta of t is identically equal to 1 for every t in G if and only if G is unimodular. Can you see that?
Can you once again repeat what is the unimodular?
Unimodular group means the left Haar measure and the right Haar measures are the same. So if you take any set which is Borel measurable and you take the left Haar measure and the right Haar measure of that, they both will be same up to a constant basically. So yeah, this is true. This is clear from the definition, because mu is a left Haar measure. If delta of t is equal to 1, then mu is equal to mu of at, right? Because that is how we define delta. So mu will also be a right Haar measure. If delta t is, so yeah, this is the one side. If delta t is identically equal to 1, then mu, which we have taken to be a left Haar measure, is automatically a right Haar measure. Now if the left Haar measure and the right Haar measures are same, then we can just substitute it here. You will get that delta of t is identically equal to 1. This is in fact why these groups are called unimodular. Unimodular means, uni means one, modular refers to the modulus function. So those groups whose modulus functions are identically equal to 1 are called unimodular. Okay. What is the second observation? Delta of t is independent of choice of mu. What does that mean? I had started with a left invariant Haar measure, but I could have started with some other left invariant Haar measure, which I know is just another constant times mu. Instead of mu, I could have started with 2 mu, which is also a left invariant Haar measure, and I could have similarly defined the delta of t. But what happens is, whatever constant c you put here, let's write it a bit darker. Whatever constant c you put here, the same constant will come here, right? And these two constants will get cancelled, and it does not affect the value of delta of t, right? So this is also not that hard. The third observation, delta of t this clearly belongs to R, what is it, R plus, right? R plus bigger than 0, positive numbers. Delta of t is always a positive number because you are taking the quotient of two positive numbers. Okay, so this equation is not always the correct equation. This equation you are dividing out by mu of a. This equation I am writing so that we have an intuition for the definition of delta of t. But the equation that we should always look at is this one. This one. Because here this is valid even if a has 0 measure. Here in this case you don't know whether you can divide by mu of a. Okay? Right.
In how measure we already choose that it is a non-zero.
No, but there can be sets with 0 measure. Non-zero measure means it is not identically equal to 0. For example, the Lebesgue measure, which we saw is the Haar measure, you have sets which have 0 measure, right? Okay. So this is true, and this is also not that difficult to see. But one of the important points or one of the important properties of this modular function is that it is a group homomorphism. Delta of ts is equal to delta of t into delta of s. Okay, what is the proof? From the definition. I'm not sure how to get it from the definition, but let's see. The proof is that you start with mu tg or ts of a is equal to mu of a ts, right? This is by definition. This is equal to mu s of at. This is again clear. This is equal to delta of s mu of at. Okay, that is how we define delta. This again I can write it as delta of s delta of t mu of a. Okay, this by definition is mu delta of st mu of a. Okay, so this delta of st equals, sorry, delta of ts, this is not delta of st, this is delta of ts, because st need not be equal to ts. But delta of ts is equal to delta of s into delta of t, right? What was the color? Yeah, tell me.
What we have to prove delta of t is equal to delta t into delta s.
Yes, that is what I am getting at. If you take a delta of ts, then we have shown that it is equal to delta of s into delta of t, but all these are real numbers. All these are positive real numbers. That is why you can write it as delta of t into delta of s. Okay, this is clear. So what it says is that alternatively this map delta from G to R plus, this map which takes t to delta t is a group homomorphism. That is what we have shown now. But something more is true. What is true is that this map delta is in fact continuous. So this is not just a group homomorphism, this is a morphism of topological groups. Instead of considering G and R plus as just groups, you consider them as topological groups. We have seen earlier, right? G is a topological group which we started, locally compact, etc. R plus is also a locally compact topological group. And what I am claiming is that this delta, more than being a group homomorphism, just a group homomorphism, it is a continuous group homomorphism. So this means it is a map of topological groups. It preserves the group structure as well as the topological structure, or it plays nice with the group structure as well as I should not say preserves, it plays nice. Yes. If I wanted to preserve the structure, then it will be homeomorphism. I am not claiming that. I am just claiming delta is continuous. Okay. How will we prove this? First thing is, observe that it is enough to show continuity at the identity. Why? If I have continuity at the identity, then I can translate it and get continuity at every other point. So just understand how important that translation maps are. Right, you can, all these problems in which you are supposed to show continuity at every point, it now reduces to showing continuity at a single point. Okay, and that is because delta is a group homomorphism. First of all, you cannot take arbitrary continuous maps and show that okay, it is enough to show continuity at identity. No, that is not true. Delta should play nice with translations, and that is what we saw. I mean, what that means is that one of the ways is that delta is a group homomorphism. So you can translate it and then you can get continuity at every other point. Right. So choose a compact set X. So we are getting into the proof of this. Choose a compact set X with a non-empty interior. X naught is non-empty and X is compact. Such a choice is possible because I have assumed G is locally compact. Okay, and so the mu which I have chosen, it is outer regular. Okay, and of course let epsilon be given. Epsilon bigger than 0 be given. So there exists a U open, again which is open, such that mu of mu of X is less than mu of U, which is less than 1 plus epsilon times mu of U. Sorry, 1 plus epsilon times mu of X. I'm sorry. This is from the property of outer regularity. You can choose open sets whose measures are arbitrarily close to x, and you can even choose it so that x is contained inside you. So we also have this, I don't think we'll be needing this, but we also have this. Okay, this is from outer regularity. Now if A belongs to x, you choose an element A which is in x, then obviously A is also in U, right? Implies U is open. There exists an open neighborhood of the identity VA which contains the identity, this is open, such that A times VA is contained in U. Why is that? Because A is an element of an open set U. There is a neighborhood, some neighborhood, which contains A and is contained inside U. Now I can translate that neighborhood by A inverse, and I can call it VA, and then I can take it back to U. Okay? But the interesting thing is, we saw in the first class that you can choose VA in such a way that moreover VA can be chosen such that A times VA is contained inside you. Why is that? Do the same argument, you take VA or you take U, translate by A inverse, get a neighborhood around the identity. We have saw in the first class that there was a proposition that if you have an open neighborhood around the identity, you can find a sub V in such a way that V dot V is contained inside U. So I will take that V, I know that V dot V is contained inside A inverse U by my construction, and I'll just multiply by A, so that I get A times V dot V is contained inside U. That V I am calling as VA. This is also not that hard. If you just take one moment to think about it, you will get the answer. Now we need to use the fact that okay, in particular A is contained inside a union of A in A. What is A? Okay, in my notes I have written X as A, so that is why. Okay, X is contained inside union of A in A times VA. Okay. I don't need this right now, I will do it later. This is okay because VA is a neighborhood of the identity. There is no capital A. Where did I write capital A? This is X. This is X.
That is U or X?
This is X. This is union of A in X. Okay. Since again VA contains the identity, A is contained inside A dot VA, and hence this inclusion is clear. Okay. Now since X is compact, there is a finite subcover. You take X is contained inside the union of I equal to 1 to n AI V of AI. Okay. Now this is a finite union. You define V to be the intersection I is equal to 1 to n VAI. This is a finite intersection of open sets and hence V is open. Okay. And also x dot V is contained inside union I is equal to 1 to n AI VAI V. Okay, because I am just multiplying on both sides. This is again contained inside U, because I have chosen my VAs in such a way that A dot VA is contained inside U. In particular, if I take a smaller set on either side, in particular if I take VAI times V, that should also be contained inside U, because V is a subset of all the VIs by definition. Okay. And so this inclusion is also clear now. A dot AI dot VAI dot V is also contained inside U. So what to do next? In fact, we can even choose V to be symmetric. V is again open neighborhood around the identity, because it is the intersection of open neighborhoods around the identity. And we have seen that V has a sub neighborhood which is symmetric, which is basically V intersection V inverse. Okay, but without going through that trouble, I will just say that without loss of generality, I can assume V is symmetric. Okay, so this is where that statement comes from. So V can be assumed to be symmetric. Okay. Now the proof is just a matter of computation. For every G in V, delta of G is equal to mu of xg by mu of x. Okay, we have shown that first of all, x should have non-zero measure, which we can assume in the beginning. Okay, because in the construction of the Haar measure we make such a choice of an x which is compact as well as which has non-empty interior, and we by the construction that we made, that we saw last time, that set will have measure 1. I could have started with that set. So this is well defined now. So delta of G is mu of xg by x. Okay. Now each of this xg's, I am starting with the G in V now. Okay. Now xv is contained inside U here. Therefore each xg is also contained inside U. Okay. And mu is increasing, right? So this I can write it as mu of U by mu of x, which we saw is less than or equal to 1 plus epsilon. Okay, this is clear, right? How did we choose U? By regularity, we had made this choice. Okay, so that is why this thing is less than 1 plus epsilon. Mu is increasing, mu is a measure, mu is increasing, so xg is contained inside U, so mu g. Okay. So one side inequality is done. What is the other side inequality? On the other hand, we have chosen V to be symmetric. Okay, right. So G inverse is also in V because we have chosen G to be symmetric, V to be symmetric. Okay, so G inverse is also in V, and since Xg is contained inside U, X is contained inside U G inverse. Yes, so Xg is contained inside U implies X is contained inside U G inverse. Okay, so we start with delta of G. Sorry, I think yeah, this is not the right way to look at it. I should have started with G inverse. Take X G inverse. Since G is symmetric, G inverse is in V. X G inverse is contained in U from earlier considerations. Therefore, X is contained inside UG inverse. UG, not UG inverse. UG. Okay. You take delta of G, which is equal to again mu of UG by U by mu of U. Again, by this, the expression on the right is not depend on the set, and since U contains X, U has non-zero measure because X we have assumed to have positive measure. Okay, UG by X, and since UG contains X, this is bigger than or equal to mu of X by mu of U, which is bigger than or equal to 1 by 1 plus epsilon. I am just reversing the inequality above. Okay, this I can write it as something like bigger than or equal to what is it, 1 minus epsilon by 1 plus epsilon, I guess. Okay, so the point is, if I take a small epsilon, so epsilon was given to me. Epsilon was an arbitrary positive number given to me, right? So if I take a small neighborhood around 1, and also so my aim was to prove continuity around the point identity, right? So what is the image of the identity? Because it is a group homomorphism, it has to be equal to 1. Identity should go to identity, right? So what I actually want to show is that delta inverse of any open set which a comma b, where a is less than 1 less than b, you take any open set containing 1 in R, in your image, then this should be open. Or it is equivalent to show that this thing contains an open neighborhood, because we are just looking at continuity at the identity. So it is enough to show that this thing contains an open neighborhood of E. Okay. Now given any interval of this form a comma b, we can find epsilon small enough such that 1 minus epsilon by 1 plus epsilon, okay, this is 1 minus epsilon, 1 minus epsilon by 1 plus epsilon, comma 1 plus epsilon, this is contained inside a comma b. We can find epsilon such that this happens, because as epsilon goes to 0, this thing goes to 1 and this thing also goes to 1. Both the left and right hand side goes to 1. and it is possible to find such an epsilon such that this happens. Okay, what we have shown is that for every g in V, delta of g is inside this interval. That is what we have shown. Okay, so what we have shown here is that delta of V, okay, this is contained inside, I mean, so for every epsilon there exists V which contains the identity, which is an open set open neighborhood containing the identity, such that delta of V is contained inside this set. Okay, another way to write it is that delta inverse of whatever, like I'll just write 1 minus epsilon 1 plus epsilon. You guys are old enough to understand that. Okay, delta inverse of 1 minus epsilon comma 1 plus epsilon is so V is contained inside this. Okay, therefore hence proof delta is continuous at the identity. Okay, so now what we have done is we have shown that delta of G is a continuous group homomorphism from G to R plus bigger than 0. Okay, what this implies is we have some nice implications. So the first corollary, which I really appreciated when I first read this, first corollary is that if G is compact, then G is unimodular. Why is that? So what was the equivalent condition for G to be unimodular? We defined the group to be unimodular if the left Haar measure equals right Haar measure. We saw that that is equivalent to asking that the modulus function of the group be identically equal to 1. Right, we saw now that the modulus function is a group homomorphism and is continuous. Okay, now if G is compact, delta of G is a compact subgroup. Why? First of all, it is a subgroup because it is the image of a group under a group homomorphism. The image is a subgroup. And why is it compact? Because G is compact and as we have shown, delta is continuous. Okay? And what are the compact subgroups of R plus? Sorry? What are the compact subgroups of R plus 0? Okay, since I will ask you to think about this, implies, so this implication is sort of a homework for you guys, implies delta of G is equal to singleton 1. So what I am asking you to prove or asking you to convince yourself is that the only compact subgroup of R plus bigger than 0 is the trivial subgroup. This is just the identity. Okay, this is something you can easily show, or I just want you to think. Okay, now this is a very nice example, and there is another thing. I mean, you can find a lot of such sufficient conditions for G to be unimodular. So in that book that I told you, right, Nachbin, he has a lot of 3-4 nice propositions where he gives sufficient conditions for when a group should be unimodular. You can look at chapter 2. I think page 77 or something.
Here r plus greater than 0 is under multiplication, not addition.
Yes, it is. It is under multiplication. It is not under addition because it doesn't even form a group under addition. Okay. Okay. Yes. So I urge you all to go and read those propositions. They are not hard. They are somewhat like the proof is like this. Just 3-4 lines you can easily understand the proof, and they give a lot of sufficient conditions for which G should which will guarantee that G is unimodular. One such condition which I will tell you without proof is that if G is equal to G comma G, this is the commutator subgroup of G, and you take the closure. You take the commutator subgroup of G and you take the closure. If that is equal to G, then G is unimodular. I mean, of course, if
you are taking any abelian group, it's going to be unimodular.
yes, yes,
That is because of finite order of 1, right? Compactness, compact subgroup. Finite.
Why?
If you take any other element in R plus other than 1,
yes,
n equal
it will
to
be
ST.
unbounded.
Yeah.
It will be unbounded. Either it will go to 0, in which case, I mean, if A is in that subgroup, then A inverse is also in that subgroup.
Comes to 1.
Yeah, then you can
Finite
make it go to infinity and it will not be compact. Okay? Yeah, that was for your exercise. Anyway, here I don't remember the proof right now.
It is a abelian group and it is a closed, it is G is a compact.
No, G is not given to be compact. Here it is.
No, G
Huh.
G comma G closure and so on.
Is that compact? I don't know. I'm not sure if that is compact. In any case, I will ask you to read that book, which is a very nice book. You can read it very easily. It's not a hard read. It's a very easy read. Okay. Now we will soon wind up with the discussion of Haar measures. But before I do that, there are some things that I would like to do. The first thing, or the first, so I'll just state some propositions without the proof, or I will give you some idea of the proof, and we'll stop for today. And the next time we will see how we can push this G, or push the Haar measure on G to certain symmetric spaces. Okay, if you remember, a symmetric space was a topological, sorry, not a symmetric space, homogeneous space. I'm sorry, homogeneous space was a topological space in which you have homeomorphisms which take every point to every other point. Okay, now these homeomorphisms, right, the homeomorphisms which make X into a homogeneous space, they form a group. Okay, and you can think of this group as acting on that X via the homeomorphisms. Okay, now it turns out that you can, this G will most probably, like in most cases, this G will be a topological group, and then you can understand your X as a quotient of that group. That is, so we will most probably see the proof of that theorem, or I'll just give you the statement of that theorem. Again the proof is available in that book. So we'll see that tomorrow. So the whole point of next class or next lecture is to understand how you can, if you have a Haar measure on G and you want to go to the quotient of G mod H, where a G mod H is not always a group. Asking H to be normal is too much. We can't always ask for normal subgroups, but still we have seen that G mod H is a homogeneous space under the action of G. So every element of G acts as homeomorphisms on G mod H, right? So we want to somehow push the Haar measure to G mod H. From the Haar measure of G, can I get a Haar measure on G mod H, which is translation invariant and all, it has all the nice properties. We will answer that question the next time, and the answer is it is not always possible. Only for certain subgroups H you can do that, you cannot do that for every subgroup H. We will partially answer that question today, hopefully. Okay, right. So the first thing, we'll stop a bit earlier today. The first proposition that I'm going to give you guys is that if you have two groups H and K, two topological groups H and K, locally compact topological groups, then the H cross K is also a group, it is also locally compact. That is not hard to show because it is a finite product. You can take compact neighborhood of one element times the compact neighborhood of the other element, which will be a compact neighborhood of the product. Okay, you call this as G. Then G is a locally compact topological group, Hausdorff, obviously Hausdorff. Everything I am doing is for Hausdorff groups. Okay. Then the Haar measure of G is given by the Haar measure of H times the Haar measure of K. So how do you do this? So this is the same way that you define product measure. If you have two measure spaces, then you can define a product measure. First you define it for rectangles, and then you approximate sets with rectangles, and then you define it as supremum, infimum, whatever. It is the way you define the Lebesgue measure on R2 if you know the Lebesgue measure on R. Okay, the same way, this is a proposition. So the actual way to write it is like this. You take the product measure of mu H and mu K, where mu H and mu K are left Haar measures on H and K respectively, and then you will get a left invariant measure on mu G, basically. Okay, now this so we saw that earlier. We saw if you have from the Haar measure on R plus, you can get Haar measures on Rn. Using this proposition, you can construct Haar measures on Rn. Okay, you will get the Lebesgue measure, usual Lebesgue measure. The proof is in that book. I am not going to give you the proof. Okay, you can refer that book, because what I want to do is leave you with some results, because this is a very rich theory. The next thing that you can do is you can study L2 spaces of these groups, etc. Because you've defined measure, you have defined integration. You know, you can make sense of integration now. If you have a function from G to R, which is measurable function, then you have a notion of integration, because you have defined Haar measure. Now you can ask for L2 functions which are square integrable, and study those spaces, and that is a very rich theory. I encourage you all to at least take a look at that theory, but we will not be going there because we have some other thing in our mind. Our target is different. So I just want to leave you with some interesting results, which hopefully you will go and, and look at the proof of. Okay, what is the second proposition today? Not today, but proposition 2 is that, okay, G is again locally compact of stuff. I'm not going to keep repeating that. If H is an open subgroup of G, this is open as well as subgroup. Okay, then first of all, mu G, which is the left invariant Haar measure on G, restricts to H. Okay, I mean this is basic topology. So what this means is that, I'll just write it as sentences. Mu G restricts to H, okay, which will give rise to a Haar measure on H. Okay, and the interesting thing is delta H of T. So if you have a Haar measure on H, you can define the modulus on H. Okay, and this will be equal to delta G of T for every T in H. Okay, so one corollary, and again you have some nice corollaries here. Acha, okay, I did not mention the important part. Here the important part is, more than this, you will have delta G. Okay, delta G is the modulus in G coming from this Haar measure of the element S comma T will be equal to delta G of S times, no, this is delta, yeah, this has to be delta H. Delta H of S times delta K of T. Okay, so one corollary of this thing is that H cross K is unimodular if and only if H and K are unimodular. Both. How can we prove this? If H cross K is unimodular, then delta G of S comma T is equal to 1 for every S and T. Okay, so fix an S and let T vary. As T varies over all the elements of K for a fixed value of S, which forces delta K of T to be equal to 1 always, or then you can even show that this thing should also be equal. So what that, okay, first what happens is this, the left hand side is identically equal to 1. That means delta HS, you fix an S and then let your T vary. Okay, then delta HS times delta K of T is equal to 1 for every T. In particular, the image of K under this map is a constant, because we will have delta K of T is equal to 1 by delta H of S naught, where S naught is the element that I fixed. Okay, this is a constant, and we saw earlier that it has to be a subgroup. Okay, because delta is a group homomorphism, it has to be a subgroup. So If it's a constant, then it can only be equal to 1. Okay, so you have shown that if G is unimodular, then K is unimodular. The same argument will work for H also. Okay, now if H and K are unimodular, then delta H and delta K are identically equal to 1, then delta G is also identically equal to 1. Okay, it is clear, right? So here we will explain a little bit what this means. Since H is open, H is an open subgroup, the Borel subsets of H are also Borel subsets of G. Okay, it is enough to just show that all the open subsets of H are open subsets in G. Of course, we are giving H the subspace topology. Okay, when I am considering H as a topological group in itself, I am giving H the subspace topology. Okay, what does the subspace topology say? And a set is open in H if it is the intersection of an open subset of G, intersection of H with an open subset of G, right? But since H itself is open, an open subset of H, let's say U, let's say U is a subset of H, and U is equal to V intersection H, where V is an open subset of G, but H is open, so U is also open. This is open in G, not just in H, it is open in G. So every open set here will belong here, and the Borel sigma algebra is generated by open sets, and therefore the Borel sigma algebra is contained inside here. Now the measure mu can be thought of as a map from the Borel sigma algebra to the positive reals, and since we have shown this inclusion, we can restrict it to the Borel sigma algebra of H to R plus. This is a measure on H, and it is translation invariant, because the translation invariant you get for free, because it is translation invariant with every element of G, it is also translation invariant with every element of H. But the regularity you should show, it is not hard, you need to convince yourself of the upper and inner and outer regular properties, but with that I will leave to you. This is an exercise in measure theory, not the theory of compact, in theory of topological groups, so I leave that to you. The next thing is that if, okay, this is the last proposition of the day. Okay, I finished a bit early today. If H is a closed normal subgroup of G, then delta H of t is equal to delta G of t for every t in H. Again the question arises, what is the guarantee that H has a Haar measure in the first place? Right. So if H were open, we use this argument and we could restrict the Haar measure to H. But here H is closed. So
It's always true.
which one?
It's always true. This equality is always true.
This thing?
We told this before.
No. No.
Something different.
This is only in this case I have told you.
This second proposition.
That is open subgroup. Here it's closed.
It has to be open subgroup here. That is the important point. That is the important distinction. Here it has to be open, but in this case, if it is closed and normal, that is enough for me. Okay? And again,
But if
before, yeah.
it is not open, then also it is true, no? Because that delta H is independent of subset, whatever we are taking.
Sorry, I didn't get your question.
I'm saying if suppose H is just a subgroup,
Okay.
not open.
Okay.
So then also it is true because this delta S is what is modulus function that is independent of set.
No,
This
no,
will
no,
be
no,
always
no.
dependent on
Delta H is not independent of this H.
That is independent of measure.
Yes, that is independent of the Haar measure we are choosing. So how did we define delta, right? So what was the motivation to define delta? कहाँ गया? We want to measure how much the left invariant Haar measure is far away from. Yeah. Yes.
Not mu.
No, no. Independent of mu we showed later here. Sorry. Okay. But what you are saying, the analogous version of what you are saying is that this is independent of G. This is what you are saying. Independent of G, which is not. This is not independent of G. Okay. What was delta H of T? It is the modulus function of the subgroup H. Right. It is the modulus function of the subgroup H. And delta G is the modulus function of the group G. Okay. Just spend some more time, you will get it. Again, as far as proportion 2 goes, we can say that if G is a locally compact unimodular group and H is an open subgroup, then it is unimodular, etc. Okay. And that is the importance of these propositions. If you have certain unimodular groups, certain groups it is easy to show their unimodular. For example, if you have a compact group, we saw very easily that it is unimodular. But if I have an open subgroup of that compact group, I mean, in any case the image is going to be one, so but that is not clear, right? So first of all, anyway, that is, I mean, it should be clear. Anyway, but that is where these sort of propositions are being used. If you have subgroups of groups which you know are unimodular, then what can you conclude about those subgroups of being unimodular? Okay. Right. So if then this is true, so there is the small thing that we should verify here is that H is also locally compact. So this is verified. This is an exercise in topology, is that if you have a Y is closed, which is a closed subset of X, which is locally compact, then Y is also locally compact in the subspace topology. More precisely, if you have a compact set K here, then K intersection Y is also compact. You don't need Hausdorff. Even without Hausdorff, this is true. Okay. So the idea is very simple. You take K intersection Y, call it, let's say, L. Okay. You take any open cover of L, union of UI intersection Y. Okay. You take any open cover of L. Now what you do, you add one more open set, which is X minus Y. This is open because Y is closed. Okay. Now this is containment. What happens is, you can show that K is contained inside this, because whatever part of K is contained inside Y, that is taken care by this, guys. Whatever part of K is contained inside, outside Y, that is taken care by this set. Okay. Okay. Sorry. These sets are need not be open. So what you do is, this is, you keep this as L. But what we can show is K is contained inside union of Ui's union x minus y. Ui intersection y need not be open in x. It is open in y, but it need not be open in x, because y is closed. Okay. But this is true. This is true by the argument that I gave you.
Ui is the open cover of
L, which is K in, sorry. Ui is not the open cover of anything. Ui intersection y is an open cover of L. This, okay, so
not open cover of L.
here I should not use. This is an open cover of L in Y. Inside Y, all these Ui intersection Y's are open. So you take an open cover inside this. Okay, is it clear?
Okay, we will see.
Yeah. So this will imply that K is contained inside this union, because whatever part of K is contained inside Y, that will be taken care by this thing. Whatever part of K is contained outside Y, that will be taken care by this. Okay, they are open, all of them are open, because Y is closed, x minus y is open. Now this has a finite subcover. This has a finite subcover. So implies K is contained inside union I is equal to 1 to n Ui. Okay. It might also contain this. Okay. But I don't care. What I want is K intersection Y, which is equal to L. This is contained inside union I is equal to 1 to n Ui intersection Y, because this part intersection will be empty. I don't need to consider that. Okay, so I have found a finite subcover. Okay, so we'll stop now. We'll meet next time. So next time I'll explain how and when we can push a Haar measure into a quotient. Okay, we'll speak a lot more about homogeneous spaces, etc.